So how is the CNN or the convolutional neural network structured? Right. In the previous sessions, which I took myself and my fellow subcord Archit, we discussed about the artificial neural network, and what the CNN actually is. It's just a build up on the artificial neural network. Like from here onwards, we see it's nothing just an artificial neural network, and from this point and backwards is what we will learn today. So just to give you a basic overview, I will be explaining like how this feature learning process happens and how are we able to extract certain features to take certain features to look at when we are going through a huge set of images, identifying if it's a cat or a dog. Again, saying cat or a dog just for example purposes. I mean, you can obviously classify, predict. I mean, you can obviously identify any object, but yeah, I'll be taking cat and dog for example. Okay. So yeah, so in the convolution, you can see that we have this step known as convolution, then pooling, then again such steps. It really depends upon the user how many times you want to do this, right? And then we have the flattening part. It's quite easy, and then we have the full connection, which is basically just taking this whole bit and just feeding it into the, I mean, just adding it up on the artificial neural network. Okay, so moving ahead, the very famous convolution operation, and yeah, so this is the mathematical expression. I will not be going into the details of it, right? But I'll be explaining a bit of the essence on what happens, right? So what basically it does is actually expresses the shape, how the shape of one function is modified by the other, right? So this is what the function convolution of operation does, right? Okay, so okay, considering the task of classifying an image, right? We have three basic things to take care of. We have three basic things that go into this convolution operation. First is the input image, right? Which is basically a set of, basically a matrix of pixel intensities. Well, it really depends what your image is like. For example, your image can be an RGB. So this would be actually a this would actually be a three-dimensional matrix in which one matrix would be accounting for the values that are present in red, the pixel intensities that are present in red, then for green and then for blue, right? And for considering black and white, and we have considered like this. For example, one means here is considered to be as black, and the zeros are considered to be as white, right? So that is about the input image. Next, we have feature detectors, filters, and kernels. Okay, so feature detector, as the name suggests, what it does is it detects features, right? Obviously it would detect features. And how do we go on? I'll just explain that in a bit. So what do we do is we take this feature detector. Okay, now you might be asking like how why one here, why not here? Well, it really depends actually. We have a huge set of feature detectors, and through backpropagation that thing is mostly taken care of. Like what sort of features do we look forward to find in a particular input image, right? So yeah, so that's taken care of. I would not want you to think over that right now. I would like to um, bring your attention to how this process is actually working, right? So yeah, so we have this feature detector. Say this for example. What we do is we place this feature detector on top of this, right? I'm just trying to make you visualize. And what happens? And what do? We actually multiply the corresponding cells, right, with each other and then add them up. For example, just take the first 3 cross 3 bit of this input image, and we have placed this feature detector on top of this. Okay, so for the first cell here, 0, 0, we have multiplied both of them 0. Similarly, so on, we go on 0, 0. Then 1 into 0, 0. And we see that this on 0 plus 0 plus 0 on multiplying and then adding them all up, we find this feature map also known as the activation map, right? And yes, and what it does, the feature map has these values like 1, 1, 1, 2, 4, for example, right? Okay, so let's see this 4. So what I can see here, this 4 came from this 3 cross 3 bit of the input image, right? As we can see that this part of the input image is a complete match with the feature detector. As you can see that all the ones line up with each other. So yeah, this is how this 4 came here into the feature map, and what it is what and the thing that this 4 is signifying here is the resemblance that the input image has with this filter in this part of the image, right? I hope I'm making sense. Whereas here zeros are defining that the input image has no resemblance at all with the feature detector, right? So this is what we get as a feature map, and we get a lot of feature maps. Like this feature detector is is actually present here, and it is identifying one such feature. For example, it is for example, again, I'll take the example of a cat or a dog. For example, cat here. So okay, so as you can see that this is one here, one here, one here. We can sort of imagine that this is a sort of a smiley face, right? What to go on about cats when the example here is quite simple, right? So there's one here, one here, one here, and then we have ones like here. Okay, so this is a smiley face, right? And what it does here, as you can see, it's not that hard. That you can see that this is the lower left part of the part of the smile that we have. So as you can see that we have 4 here, therefore we can see that the bottom left part has this feature. And what do I mean by feature over here? The part of the smile, the left part of the lips actually, and the nose, right? I hope I'm making sense. Right, guys? Can I get a quick yes if I'm making sense to everyone? Hello?
Yes, go ahead.
Okay.
Hello. Yeah,
Go ahead.
Yeah, okay, sure. Yeah, okay. So that's how the convolution operation takes place, right? Okay. Then again, a quite a normal question. I mean, even I had this question in mind, like why to do this at all? Like why are we just doing this? You know? Well, one thing is that we are actually reducing the size of the image. As I told earlier, that we had the problem of computational power. So yes, we are reducing the size of the input image, and you can see as well that we are not actually losing. We are losing. Definitely, we are losing a bit of the information, but we are not losing. We are not losing information in the sense that we are not actually able to. We are not actually able to have the features. Like we are not actually able to. For example, just take this example. Like we did remove some of the data from this. For example, you can see that the dimension of the matrix has reduced, but we are still able to see that this feature over here, that means the bottom left part of the input image is resembled. I mean, it is a match. Therefore, we have a bottom left. We can say that we have this feature in the bottom left part of the image. Therefore, we have lost data, but actually it is good. We actually have optimized the number of parameters that we'll see later on that are to be learned. Even though we know that such a feature input image. So yes, we have brought down the size of the input image. We have lost information, but that's for the good. And okay, one more thing is through convolution, we are able to bring this property known as translational equivariance, or can simply say as equivariance. And it is quite an important property, as oftentimes it happens that a particular object in an image is present towards the extreme left or the extreme right, or even in up or down, somewhere around, not in the center. Not always necessary that the object that we are trying to detect is present in the center. So what it takes in account for that is that we are not losing, we are actually not losing the feature that is present. I mean, obviously, if the image is shifted to a bit towards the right, obviously we have to identify the feature that it has, even though it has shifted. So yeah, this is one great property that the convolution operation possesses. And yeah, I would say that it really helps in building the CNN, to not be very sensitive towards data. For example, even if you shift the data, shift the image a bit towards the right or the left, then the model is, just falls apart. No, we actually, through this convolution, we are bringing that flexibility in the model, that even though the image is shifted, we are able to identify it. And this is just for example's sake, that this image of very famous Jeffrey Hinton convoluted with this filter, we are getting some sort of this image. Right. Moving on. Okay. So these are again examples wherein on taking different types of filters, we have different outputs. For example, in taking this matrix, we have the Taj Mahal, the picture of Taj Mahal sharpened here, blurred. Here we are detecting edges, right? So yes. So okay, so by now um, we are able to bring this property of equivariance into our model, and we are also able to uh, uh, we are also able to reduce the size of the input image, right? So we have done quite a bit. Okay, so one more step that we have more steps, and the second step is pooling. Also in this research paper, it is referred to as sub-sampling, right? So what happens in pooling? Um, so poolings is mainly of three types: max, min, and mean pooling. Or what it does is quite simple. I'll just explain in a bit. Uh, right. So again, we take a 2 cross 2 box. Okay. So we take a 2 cross 2 box and we place it over the feature map, right? The feature map that we just obtained. Um, uh, Here, the feature maps that we just obtained over here, after convolving it with the filter, after convolving the input image with the filter, the feature map. Now we further process this feature map, and through the process known as spooling, and we take a box, and the size of this box is usually depends upon the person who is model, right? So we take this 2 cross 2 box, put it on top of the feature map, right? And then we account for example, here we are doing the process of max pooling. So all the cells that come within this 2 cross 2 box, we take the maximum value of the cell, right? For example, 0011, right? The maximum value of all these cells, amongst all these cells, is 1. So we take here 1, right? And then we move these 2 cross 2 boxes forward, and there's a term known as stride. And what basically stride means is the amount of units that you are shifting this box towards the right or in the x direction. That is basically stride, and the amount of units that you're shifting the box in the y direction, that is actually the y component of stride. So basically stride has x and y components, right? So for here we have the x component of stride taken as to be 2. So for here we first place that box over here, we get value 1. The maximum value amongst all these cells is 1, and then we further move ahead and we have this part of the feature map which has maximum value as 1, and then we further move ahead and we have, since there is nothing here, therefore we'll just take the maximum of these two values, which is again 0, and yes, we move on. Then we have a stride of 2 in the y direction. So the box initially was over here, so we have in the y direction we shift 2 units towards the down, so towards the downward side. So now the box is over here, and now we take the maximum value of amongst all these values, and we have 4, and so on. We have a pool. Okay, so that is how the pooling the process works. And similarly, in case of min pooling, we are basically taking the min value, and in the mean pooling, we are taking the average over all these cells that are being comprised by the box, right? Okay, so the essence of this pooling, or like why are this pooling operation after all? Okay, so pooling provides a property known as approximate invariance, right? Because in the end we want to build a network that is capable of detecting the object and the image without being confused over the differences that there are present in the image texture, or the place from where the image is being shot, or the angles, etc., right? So the reason we extract, for example, here in maximum pooling, we are taking the maximum value. Like, why are we doing so? Well, we are doing so that we want the model to we actually want to increase the flexibility of the model even more. Apart from the translational equivariance, we want the model to account for distortions as well. So for that, we have this process known as pooling, wherein it discards some of the part of the feature map. For example, here it is guarding around 75% of the data present in the feature map, and accounting for the most dominant feature, right? So yes, so it actually takes case of both of those things. So one being the same thing, the problem of having distortions in images, and making the model flexible to even account for that, as well as we are again reducing the size of the feature map, and hence getting over the problem of having the data being overfit to our model, right? So okay, so why I have written approximate invariance here, because actually uh, we cannot completely, full-fledgedly be able to bring in that that property of invariance. Uh, we only can do we only can have this property of invariance up to some extent, but yeah, that's a limitation of a CNN, and that we cannot you know make the model completely invariant. Okay, so by now we have this model where we have done the convolution, we got our convolution layers which have all these feature maps. Then we have done the pooling part, which will take into consideration the distortions present in the image, and we have our pooled feature maps, and this is known as the um, pooling layer, right? So moving on, our second last step, the third step, the flattening part. So it's not quite difficult. I mean, it's just straightforward process in which we have a pooled feature map and then we flatten it and we get a column vector. And so that's basically it. We are basically preparing the pooled feature map. We are basically preparing um, uh, the features that we have extracted through our previous operations, and then we are just preparing it to be fed into the artificial neural network, the simple artificial neural network that we have studied previously, right? So yeah, it's basically turning this feature map into a column vector, and then pushing that into a CNN. Right. And the last step is just basically stacking it all on top of the artificial neural network, where we have done the convolution operation, and then we have done the pooling operation. And in the convolution operation, we have taken care of the equivariance part, and in the pooling operation, we have taken care of a bit of distortion and some sort of approximate. We have brought about the property of approximate invariance, and after that we have flattened the data and then fed that into the artificial neural network. So this is how the CNN as a whole looks like, right? So in this paper there were actually three ideas presented by Professor Jan LeCun, and uh, he explained like how is this approximate invariance and this equivariance is brought about in the convolution, in the model of convolutional neural networks. So the first one was being the local receptive fields, right? So what do I mean by receptive fields? Like okay, so the what happens is a neuron is actually only exposed to certain regions in the input data, and not actually connected to all the parts of the input data. For example here we have all of these connections made. So what happens through the local receptive fields is that a neuron triggers only when it identifies certain sets of features in the data. So yes, that is one thing. And what that does is it decreases the number of connections within the network, and thus reduces the weights and biases to some extent, and the computation resources aren't compromised. Okay, moving on, we have shared weights, also known as weight replication, right? Okay, I'll go over through this through an example. Like we have here these images of cheetahs. Okay, so why cheetah again? Because cheetah is my favorite animal. Okay, so yeah, so right, we can observe like all of these cheetahs has this line. This line over here, this black line known as tail line, and it is pretty much like an observation that whenever we see a cheetah, we have this feature that a cheetah possesses of having a tail line, right? Although in different images, this the orientation of this tail line might differ, might vary, but yes, a tail line is present in every cheetah. I mean, yes, obviously. So okay, now coming back to what happens is. We are effectively during the learning stage. For example, we have to identify an object. We are um, for example, in we have we have a huge set of data, and we want to identify human faces from it. And for example, if I'm looking for an eye, and if I'm looking for an eye through so it is quite intuitive that I'll be using the same filter. I will not be using different filters for identifying an eye in different images, right? That's quite obvious. So and since through different and since and each part of these of the filters, just a sec, um, each part of these filters or the feature detectors would have some weight and biases associated with it. So um, therefore it really is, I don't think there is a need to have different feature detectors for detecting the same sort of features. For example, just take the case of having of the tear lines in the cheetah. I don't think that we require any other um, feature detector for detecting the same tear line within different images of cheetahs, right? So yeah, that's quite obvious. So well, that saves us a lot of time in, because a single weight and bias, I mean, a single set of weight and biases for the filter usually accounts for all of the tear lines that are present in the cheetahs, right? So through this, the weights are shared, and therefore the time taken during the back propagation step is reduced. Okay, so one might ask that why do I not use shared weights? So again, the problem is that we would not actually be ending up with desirable results, and um, actually it is important to use the same filter, because we really need to have that condition of equivariance, because obviously the tear line might be located in different parts of the image. For example, we can say it's located a bit towards the middle right, and from here it is towards the extreme top and yeah, so if we have different filters, it would give us bogus results, and therefore I mean, one common filter is just important. So we are just reducing the total number of weights that are to be optimized during the back propagation step, as well as we are achieving the condition of equivariance, right? The third idea that he proposed was the spatial, the temporal subsampling. Okay, so what it basically means, the pooling process that I just explained, that and I would not like to repeat myself, but it's basically the pooling process wherein we take in account for a bit of we are building a model that is flexible enough to account for that provides approximate invariance to translation, and as well as it reduces the dimension of the parameter space of weights and biases. It reduces that as well. So yeah, okay, I'll end.
Hello,
Yeah,
hello.
go ahead.
I had a doubt.
Yeah,
When
yeah,
do we
sure.
use while we use pooling? That you said there are three different types of pooling: min, max,
Uh,
and average. So, are there different scenarios where we use all these type of pooling, or is it just computation? We get the computational value and we decide which one is better.
Okay. So, yeah, for sure. Yes, there are different. Actually, it really depends upon um, mostly like what sort of feature map you end up over, what sort of input you have over here. For example, this what I initially said was this one accounts for this pixel being black, right? And the zeros account for these pixels being zero. So what max pooling does is just consider the example of what would have happened if we did the process of min pooling. Could you tell me?
Yeah, we would have taken zeros here, and then
Yes, and what
we
does
might
zero
have
account for? Light
white.
pixels. Yes,
Yeah,
white pixels, exactly. So that would not, I don't think that would be something that you
yeah,
would like to do, wouldn't it?
yeah.
Yeah, so does
So
that
it
explain your
gives the
question?
completely different kind of results than what you were
Exactly.
planning for.
It is basically up to you, If your image is, for example, if I just invert the scenario over here, and if I say that the zeros account and white account for the light pixels, I mean the white pixels, and the ones account for the white pixels, then what kind of pooling would you like to use?
Uh, yeah, the min max pooling would be better case here.
The min pooling, I guess, right?
Yeah.
I
Also,
mean, like
okay,
obviously
fine.
we'd
If
have to
image
change the
is,
values of zeros and ones, but you get the idea,
hmm,
right? It basically
yeah,
depends
yeah.
upon the input image. Yeah.
Hmm.
Okay. So is that clear?
Yes,
Right.
thank you.
Okay. So I'd like to conclude today's session with discussing about the problems that we still have in CNNs. Obviously, we haven't reached perfection. We will never will. We never will. But one of the problem is this first one of having pooling layers, as I said, that uh, we do lose a lot of valuable information, right? Okay, now again I'm saying a valuable information, and initially I was saying that no, it's fine losing information, but try to understand like what's the case here. Well, the case here is that during pooling we actually aren't considering the image as a whole. We are basically identifying individual parts of the image. For example, if we just consider just consider this, that we have this one image and this second image, and we are feeding it into a trained CNN, and what will happen is that the CNN would identify both of these as human faces, right? Because according to CNN, in the process of pooling, we basically are just identifying for if a particular image has two sets has two eyes, in some sort of like this, has a pair of lips, and has a nose and has a face structure somewhat like this, and therefore it's a face, right? So I don't think that would be just the right criteria to identify a face, because obviously this isn't a face. Like, you need to have the eyes over here, like that. So this is one problem that CNNs do face, right? And the second problem that I would like to mention over here is the problem of rotation and orientation. Like, for example, consider this, like I did say that we can account for to some extent, if the images are rotated, we can go on classifying that image correctly, but extreme cases, no, it really imposes a problem on the model, that on the rotation aspect of the input data. So yes, these two problems I'd like to mention. Right. So that's my side. If you have any questions, I'll be open to answering them. So please shoot. Are there any questions?